one of the things the chair has to do.
Yeah.
Interrupt the speaker if somebody is typing in a question for you.
Yeah.
Of course, I
Gayatri is
can
also,
keep a chat window open in the corner here.
You can? Oh, you
you
just,
can.
okay.
Yeah, I just did that.
I mean, you can see it simultaneously, like while you're presenting, you
Yeah,
can
yeah,
still.
it's on my screen. Yeah.
Oh.
It just covers a part of my writable surface. So.
Oh.
Yeah, you don't have to do it if you don't want. Yeah, but it's your wish. Yeah.
Sita, your volume is a bit low. So,
My volume?
I mean, your
Okay.
voice. Yeah. You may need to be closer to the phone to speak or something.
Okay. Let me just increase my mic volume a little bit. Is it better now?
A bit too high. Probably.
It's bit too high. Okay.
Yeah,
I
this
think
is
Okay.
good. This is good.
Okay.
Okay, just not.
I'm just going to turn off my audio and video.
Okay.
So, should we slowly begin?
Yeah. Yeah. Or should we wait for a
Well, I'll
couple of
give an
minutes?
introduction to IMSc and things.
Okay. Okay. Um, 1 minute. So Welcome everyone to Facets, which is an annual outreach program of IMSC. It's typically a 2-day event organized in IMSC, and everybody comes and we sit in the auditorium and have it. But this year being special, it's delayed and it's online. So it's a special time. Online talk is not half as interesting. And also thanks for the speaker who's going to try and make it as interesting as an online talk can be. Um, uh, yeah, so over to Professor Amritanshu Prasad, who does mathematics in IMSC. So he will uh, tell you a bit about IMSC before proceeding to give his talk, which is titled Cycles of a Random Permutation. So over to Amri.
Thank you, Sushmita. So it's not we usually like to have all of you over to math science where we can meet you and talk to you and so on, and it's not unfortunately possible this year, but we decided to go ahead with this program anyway, and I must thank Sushmita for making all the arrangements. So what I'd like to say is that if you want to ask any questions at any point, you can just unmute your mic and ask me. Just keep it muted at other times. It's going to be somewhat informal. If you want, you can keep your video on if you want to be seen. Um, that's fine. I like to see faces of the audience members, but if you don't, that's fine too. Um, so Sushmita asked me to say a few words about IMSC before I begin. So IMSC, the Institute of Mathematical Sciences, is many of you would have seen it, but if you haven't, it's a small research institute located just off OMR near Adyar, and we have basically PhD programs and integrated PhD programs in mathematics, theoretical computer science, physics, and in computational biology. And these are it's entirely a theoretical institute. All the work we do is we don't really have any labs and so on, though uh, we do interact with places which do experimental work. And you can find information about our programs, how to apply, how to get admission, and so on our website, which where all the information is there. If you have any questions about those things, you should feel free to write to one of the faculty members who are close to the area in which you want to work. We also have summer programs, visiting student programs, and so on. Students often come here to do summer courses depending on the availability of faculty. We also have a large library, which is usually open to public. Anyone from anywhere can walk in. You just need to show your university or workplace identification card to use the library for reference. But right now, because of the COVID restrictions, the library unfortunately is closed. So we hope that when things get better, you will all try. Some of you will come and visit us, and maybe hopefully next year this program will be, you will be able to visit math science for this program. Okay, so with that out of the way, let me talk about some mathematics, and this is I'm going to talk about cycles of random permutation. uh, I suppose you can see my slides. Well, I'm going to just use this thing to write on. And this picture here you see is it depicts a permutation of, yeah, so this depicts a permutation of numbers 1 to 9. The way it's shown is in terms of arrows. So in this permutation, 1 goes to 4, 4 goes to 7, 7 goes to 3, 3 goes to 9, and 9 goes to 1. 2 goes to 8, 8 goes to 2, 5 goes to 5, and 6 goes to 6. And this way of depicting a permutation reveals what I call its cycle structure. I'll go into the details of all these definitions soon. But the theme of this talk is that you take a random permutation, which means that you choose a permutation randomly in such a way that each permutation has the same probability of being chosen. And we would like to understand what the behavior of the number of cycles of different sizes is in such a random permutation. So that's roughly what I'm going to talk about. Don't worry if you didn't understand what I said. I'm going to explain everything in great detail uh, soon. And it turns out that these cycles, the distribution of the number of cycles of different sizes will follow what is called a Poisson distribution. Those of you who have taken a probability theory course may have heard of the Poisson distribution. It's a beautiful thing. So I'll start with that. So yeah, let me start with the Poisson distribution. So this so there are a few things that, you know, when you have randomness in life, there are a few distributions that are very common, which occur very commonly. One is the Gaussian or normal distribution. I'm sure you've heard of the bell curve. And um, another is the binomial distribution, which looks like a discrete version of the bell curve. And another, perhaps the third most important distribution, is the Poisson distribution. So this is a so what you do is it comes up, for example, when you have if you have a bunch of like radioactive material and it decays, so you have radioactive decay, or you have to be more topical, you have a bunch of coronavirus, and you know, this virus, if it's on the surface, it slowly dies out, and the the number of atoms, so if you're talking about radioactive material, the number of atoms which decay in any given time unit, say in 1 second, or the number of viruses which die every second, these are the kinds of things which follow a Poisson distribution. So axiomatically you could say that you have a sequence of random events occurring in time. So, like each time an atom decays, that is one occurrence of this random event. So, you have this event occurs, and then you wait for some time, and there's one more occurrence, and so on. Or each time a virus dies, it's an event. Now, the assumptions of these random events occurring in time is that the conditions do not change with time. So for the examples I'm talking about, this is true on short time scales compared to the half-life of the unstable isotope or the virus. Okay, so of course, if you wait for a long time, then the amount of radioactive isotope or alive living virus reduces, and so the rate of decay will also decrease. But if the time scale that you're studying is short compared to the half-life, then this assumption that the conditions do not change with time is valid. And the second axiom is that uh, non-overlapping time intervals are stochastically independent, or which means that suppose I take the time from now to 1 second later, and then I take a disjoint time interval from, say, 5 minutes later to 1 minute after that. So I take these two disjoint time intervals of 1 minute each. Whether an event happened in the first time interval or how many events happened in the first time interval has no bearing on whether another event would happen in the second time interval. Or so in that sense, uh, non-overlapping time intervals are independent. Okay, so information about the number of occurrences in one interval does not affect the what you expect to happen in another interval. And we'll also fix a parameter for this problem, and that's lambda, which I will call the rate of events per unit time. So this is like how many events do you expect per second or per whatever unit time unit you fix. Okay, so these are this is the axiomatics, and from this we can derive the Poisson distribution uniquely. So if you have this, then you can say that the number of events. So let x equal to number of events in one time unit. This x is distributed according to Poisson distribution with rate lambda. Okay, so I'll derive the probability distribution function for the Poisson distribution just based on these axioms. At this stage, do you have any questions? Please do not feel shy to ask. You can just unmute yourself and ask if you have any questions. Or at any point of time, and if you want, you can just type your question into the chat. So, I'll read it and answer. Okay, so no questions? Okay, so let me then continue. Okay, so let me just describe this. Uh, yeah, let me just derive the probability density distribution function for this Poisson distribution. So the way we'll do it is we will kind of take a discrete approach. So it's just somewhat simpler. So what I'll do is, uh, yeah. So let's look at this one time interval. So we have a time interval from 0 to 1, and I want to see how many events occur inside this. So what I'll do is I'll just divide it into small pieces, uh, each of size 1 by n. Okay, so this is 1 by n, this is 2 by n, this is 3 by n, and so on. And if n is sufficiently large, then it's unlikely that two events will occur inside one of these small subdivided intervals. So if n is sufficiently large, it is unlikely that more than one event will occur in any of these subintervals. Because it's a small subinterval. So we have this rate lambda, and we are expecting about lambda events to occur in this interval. And if n is very large compared to lambda, then it's very unlikely that more than one event will occur. So we can think that, okay, in each of these intervals, either an event occurs or it doesn't occur. But what's the probability that an event would occur in each segment? And that's, well, okay, so over this whole thing, you expect lambda events to occur. So in each of these subintervals, you would expect about lambda by n. Probability that an event occurs should be about lambda by n. So this we can say should be lambda by n. And in these intervals, the occurrence of events are independent because we have this axiom that disjoint intervals are stochastically independent. So these intervals are independent. Subintervals are independent. So we are in this situation where we have what are called um, uh, Bernoulli trials. So each each interval is like a loaded coin, a coin where the probability of heads is lambda over n. And we flip this coin, and if it's heads, then we say, ah, an event has occurred. But if it's tails, then we say, okay, no event occurred in this interval. And then we do this, and then we count up the total number of events that have occurred over the full, all in the sum of all these intervals. And that many of you would know is what is called a binomial distribution. So, so what we have is that the probability of uh, k events occurring is the probability that k of our loaded coin tosses turned up heads. And the probability of heads is lambda by n. So that is, you choose which k of them, and then based on that, you have lambda by n to the power k. That's the probability of those k turning up heads, and then the complementary probability to the power n minus k. And we'll put an n here to just denote that we have divided the thing into um, into n subintervals. And then what we do is we take this subdivision and make it finer and finer and take the limit. So limit as n tends to infinity of Pn of, I'll call this k events occurring as x equal to k. So x is the number of events that occurs. A probability that x equals k is going to be the limit as n goes to infinity of n choose k. So let me just write that it's n factorial by k factorial into n minus k factorial. And then I have lambda to the k by n to the k, and then I have 1 minus lambda by n to the n minus k. And if you just try to evaluate this limit, let's see if there's some cancellation. So this term can be written as n into n minus 1, sort of falling numbers, k of them starting with n. So this is n into n minus 1 up to n minus k plus 1 divided by k factorial, right? I took out the n minus k factorial. And this in the limit, this each n minus I, since k is fixed, n minus I is very close to n. So here there are k terms which are like n, and here there's n to the power k. That will cancel out in the limit, okay? And then we have lambda to the k by k factorial, and then we have limit as n tends to infinity, 1 minus lambda by n to the power n minus k. But again here, n is very large, k is fixed. So this, and this thing is close to 1 as n is, when n is large. So this is just like 1 minus lambda by n to the power n. And so you know that that limit is e to the power minus lambda. So what you get is, this is lambda to the k by k factorial e to the power minus lambda. This is the probability distribution function for the Poisson distribution. The sum that the probability that k events occur is e to the minus lambda, lambda to the k by k factorial. And you can easily check that these probabilities add up to 1 if you take the sum from k goes from 0 to infinity, as expected for probabilities. Okay, so any questions so far? So, So for example, what's the probability that x is 0? So that's just going to be e to the power minus lambda, right? Okay, so that's the Poisson distribution. Okay, so I just want to do one more calculation with this Poisson distribution, and it is this. So what is the expected value of this number of events? So as I already told you, it is lambda, but let's just think of this in one more way. It's like when you have a probability distribution. So expected value under Poisson lambda of x. So what does this mean? Well, by definition, it is the sum over all k. In this case, these are the possible values that the random variable x can take, and then the probability that x equals k multiplied by the value of x. So that is k. And so in this case, that is just summation k goes from 0 to infinity, k e to the minus lambda, lambda to the k by k factorial. And what I can do is I'll pull out this e to the minus lambda here. And I'll cancel out this k, and I'll make this k minus 1 factor. So you just have this, and that of course um, you pull out a lambda as well. So this is lambda e to the minus lambda summation. And now this again, just re-indexing, this is lambda to the k minus 1 divided by k minus 1 factorial. So this is again lambda to the k by k factorial. And that cancels out with this e to the minus lambda. And so you get lambda as expected. Okay, so we set up the thing to have expected value lambda. But let's look at, let's try to find out what is the expectation of x squared. Okay, so what is the expected value of the square of a Poisson random variable? And this is by definition, this is the sum k equals 0 to infinity. And then here we, instead of putting k, we would put k squared lambda to the k, k factorial. But this is slightly awkward in the sense this k squared doesn't cancel with this k factorial. So it's slightly easier if instead I compute expected value of x into x minus 1. So then that will be k equals 0 to infinity, k into k minus 1, lambda to the k by k factorial. So that's just going to be, if you just, then now two of these terms will cancel out. And oh, there's also an e to the minus lambda here. And what you'll see is that you will get lambda squared will get pulled out. So you'll get lambda to the k by k minus 2 factorial. And this turns out to be lambda squared. So this expectation of x times x minus 1 has a simple expression. And using expectation of, now you can compute expectation of x squared as expectation of x. You know, this expectation is a linear map. And so this is expectation of x times x minus 1 plus expectation of x. So using that, you can compute the expectation of x squared. But I'll just be happy with this, because if I know expectation of x and I know expectation of x to the x times x minus 1, I can compute expectation of x squared. And similarly, if I want to compute expectation of x cubed, instead I will compute expectation of x, x minus 1, x minus 2. And that will turn out to be lambda cubed by a very similar um, calculation. And now the more general statement is the following. So define x parentheses with a subscript r to be what is called the falling factorial. So it's like x into x minus 1, and you take a total of r terms. And then the expectation of this falling factorial turns out to be, so if you just look at the previous calculations, you can guess, and then you can easily compute lambda to the power r. And this, so here's the point. So why am I saying all this? These things are called moments. So expectation of x, expectation of x squared, expectation of x cubed. These are called the moments of the Poisson distribution. And it turns out that these are certain invariants. Well, these are certain invariants associated with the Poisson distribution. But it turns out that the Poisson distribution is the only probability distribution which has these moments. So that's a well, that's a theorem. It's not completely obvious. So if x is a random variable, that means it's some randomly occurring real number taking values, but it doesn't actually matter what values it takes. And we have that expectation of x. Now, expectation of x, uh, these moments are also determined by the moments of x1, x2, x3. So these falling factorials. Expectation of x to the r is equal to lambda to the r for all r greater than or equal to 1. Then lambda. So there's a certain uniqueness statement here. You may have seen a result if you've taken a course in probability theory involving characteristic functions, but there's also a similar result. It's not true for all sequences of moments, but for certain sequences of moments, it's a unique probability distribution with those moments. And this is called the method of moments, determining a probability distribution from its moments. Okay, so all of you seem to be very quiet. Any questions? Am I
No, sir.
talking too fast?
No, sir, not yet.
Okay, thanks, Nishant. All clear? What I'm saying?
Yes, sir. Till now, all clear.
Okay, thank you. Anybody else? I mean, if it's not clear, just because Nishant finds it clear doesn't mean that. So, okay, so let's see. So that's this has nothing to do with permutation so far. So let's come to permutation. Um, so what's a permutation? So so let's just use this notation box n to denote the set 1 to n. And a permutation is a bijection from n to n. I'll denote it by sigma from n to n. And I'll show you a nice way of getting a permutation now. So here in my hand, I have some playing cards, and I have taken from the deck all the spades. Okay, so I have all the spades here, and I'm just going to the 13 cards from the ace to king, and I'm going to just shuffle these. Okay, so I'll shuffle these, and then I can just shuffle them really well. And now these 13 cards are in some sort of, they're in a random order. I do not, it's completely random. And the number of possible orders I can get on these cards, ways of shuffling these cards is 13 factorial. And I can just tell you the order in which these cards are appearing. On right on top I have 4, and next to that I have Jack, which I will say is 11, and then I have 3, then I have 10, then I have 7, 9, 5, King, which I'll call 13, 2, Queen, which is 12, 6, Ace, which is 1, and 8. So let's see how many have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Good, I have all my cards here. So this is an example of a random permutation. You just take a deck of cards and you shuffle them, and you have, if you take the full deck, then you'd have a random permutation of 52 things. So n equals 52. So here's a nice way to generate a random permutation. Alternatively, you could just write a computer program to generate one. There are interesting algorithms to do this. But okay, so let's see what the cycle structure of this thing is. So to see the cycle structure of a permutation, you just write down the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And now this thing, the way I've written it is that it means that the first thing was, in the first place I had 4. So I'll write this as 1 goes to 4. Okay, so 1 goes to 4, and 2 goes to 11, and 3 goes to 3. That is, whoops, I want a full circle here. 3 goes to 3, 4 goes to 10, 5 goes to 7, 6 goes to 9, 7 goes to 5, 8 goes to 13, 9 goes to 2, 10 goes to 12, 11 goes to 6, 12 goes to 1, and 13 goes to 8. There's 13, 13 goes to 8. So you see this graph that we've got a directed graph here, and it has the property that every node has one in edge and one out edge, and we can look at the connected components of this graph, and these are precisely the cycle. So we start with 1 and we look at what happens. Then we have 1 goes to 4, 4 goes to 10, 10 goes to 12, and 12 goes to 1. So that's what I would call a 4 cycle. Now let's look at 2 is not in this 4 cycle. So let's look at 2. 2 goes to 11. 11 goes to 6. 6 goes to 9. 9 goes to 2. Okay, that's another 4 cycle. And then let's look at 3. That's all by itself. It's a 1 cycle. And then 4 is already in this cycle. 5 and 7, they form a 2 cycle. And I think 4, 8, 10, 11. So I'm missing one more 2 cycle. I think that's 8 and 13. So I just took these pieces of this graph and separated them out. And now I have a clearer picture of how this permutation moves things around. So I'd say that the cycle type of this permutation, let's call this thing sigma. So the cycle type of sigma is 4, 4, 2, 2, 1. So it has a 4 cycle, another 4 cycle, a 2 cycle, a 2 cycle, and a 1 cycle. So this these things add up to 13, and I've written them in decreasing order just for should fix some convention. I don't want to distinguish between. I have no. There's no natural way to say which is the first cycle. I mean, I guess you could say that the cycle with 1 is the first cycle, but that's not my concern. So I want to not distinguish between the order in which the cycles appeared or anything. So I'll just write them in decreasing size just to fix a certain convention, so that I know when two things are the same or different. So these are the permutation. This permutation has cycle type 44221. And another convenient way of writing this, so this is called a partition, is a partition of 13. And another way of writing this is in terms of the frequencies. So this is 1 to the power 1. There is one cycle, 2 to the power 2, and 4 to the power 2. So this is what I call the exponential notation. So more conveniently, so let me just write down partition. So partition of n is alpha equals alpha 1 alpha something L, where alpha 1 is greater than or equal to alpha L, or they are in decreasing order, and their sum is n. And then we have the exponential notation. And so on, if the number of I such that alpha I equals j is aj. So these are the frequencies of the different uh, sizes of the cycles. So here I had omitted, I could write here 3 to the power 0 also, but since there are no 3 cycles in this permutation up here. Okay, so this is a random permutation, and it turned out to have 5 cycles. It turned out to have 1 3 cycle, 2 2 cycles, and so on. Let's just see how many cycles a really large random permutation has. Okay, so I hope you understand now this notation that I'm talking about here. I'm taking a random permutation. This one I generated using my deck of cards. Maybe you can think of other ways to generate a random permutation without a computer. And with a computer, it's again very interesting. But you can do it with the computer. I'll just show you how to do this. So I use this software called Sage. Um, Let me just show you here what I'm doing with Sage. So, so this is a Sage terminal, and I just typed this one command here. Well, it's a rather long command. Maybe it could have been. So let me just show you. So I can construct in Sage W equals permutations of say 100 and ask for a random element of it. Okay, and so this is W. This is a permutation of 100. So 1 goes to 41, 2 goes to 1, 3 goes to 61, and so on. And then I can ask for W, its cycle type. It's, yeah. So it turns out that it has a 59 cycle, a 27 cycle, an 8 cycle, 1 3 cycle, 1 2 cycle, and 1 1 cycle. So now what I'm going to do is I'm going to take 10,000 permutations of 100. Okay, so I have here this thing here says for n in range 10,000. So I'm going to do this 10,000 times. And I'm going to take a permutation of 100. I'm going to take a random element. I'm going to take a random permutation. I'm going to take its cycle type, and I'm going to write it in exponential notation. And then I'm going to take the sum and divide it by 10,000. So what that will give me is the frequency, the expected number of the average number rather of 1 cycles, 2 cycles, 3 cycles, and so on. So here you see that the average number of 1 cycles is turns out to be 1. The average number of 2 cycles, well, it's close to 1. So it's plausible that it is 1. Maybe if I do, 1 lakh trials or something, it will be closer to 1. The number of 2 cycles is 0.49. That's pretty close to half, right? And the number of 3 cycles, that's 0.335. That's pretty close to 1/3. And the number of 4 cycles, that's pretty close to 1/4. This is pretty close to 1/5. So it's not bad at all, the approximations, right? So what we're seeing, in fact, the 100 cycle is close to 1 over 100, 0.001. So it's pretty good. Huh? And so what we see experimentally, yes, mathematicians also do experiments. I said we don't do experiments in math science, but I do experiments like this. Um, so yeah, so we do experiments on the computer, and what this experiment suggests is that we would expect about 1 over I cycles in a random permutation of large n. Okay, so that's the observation that you get from there. So
can we run that experiment again, please?
sure, why not? Looks suspiciously similar, no? Well, okay, it's not exactly the same, yeah. Yeah, and you could average these two if you want. That's the average of the two. It's getting better and better. Well, maybe not. Okay. At least this thing is 0.48 is a little disappointing. Here we had 0.49. Anyway, so that's still, the numbers are pretty good. So you wonder what's happening, and so it turns out the main result that I'm talking about is say that the number of I cycles in a random permutation is going to be distributed Poisson with expectation 1 over I. And the number of 1 cycles, the number of 2 cycles, the number of 3 cycles, these are all independent of each other. And the condition here, of course, this is only for large n. So this is a convergence result that for very large n, the number of I cycles is distributed roughly Poisson, Poisson with expectation 1 over I. And the 1 cycles, 2 cycles, 3 cycles, and so on are independently distributed. And I'm not going to give you a fully rigorous proof, but I'm going to reduce it to the method of moments and then give you a bunch of references you can look up to finish the proof. But this will give a fully rigorous proof if you do all the work. But so here the method of moments, you remember, where did it go? Yeah. So the method of moments said that as far as moments goes, if it looks like a Poisson distribution, then it is a Poisson distribution. Right. So that's what I'm going to show, that these limiting distributions for um, the number of cycles, their moments will look like Poisson moments, joint, yeah, mixed, what called mixed moments. So that's one calculation that we need to do, and the only calculation that we need to do. So this calculation kind of came up naturally in my research, and then later I realized that it's known to people who work in random permutations, but it came up in another context, in the context of representation theory problem. So here's the question. So so we will try to compute expectation of. So let's say xi equal to number of I cycles in a random permutation. And so here when I say random permutation, uh, we will say we will have to specify what n we are taking, and then we'll be interested in the limit as
Yeah,
n goes to infinity. Yeah, question?
actually, we can't see your screen.
Oh
I mean,
yeah, that's true. Good point. Uh, I thought I started sharing it again. Is it working now?
yeah, 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 yeah.
Oh, I think I was sharing the other thing still. Yeah. Okay, so let xi be the number of I cycles in a random permutation, and I'll leave this symbol sort of without specifying what n is, but when I talk about the probability, I'll try to fix n. So what I'll say, so what I want to compute is what is the expectation, and now I'll put an n when I mean that you choose the permutation randomly from permutations of n. And then what I want to know is what is x1 to the b1, x2 to the b2, x3 to the b3. So this is what is called uh, a mixed moment. So we will show that as n goes to infinity, these will go to the mixed moments of Poisson, independent Poisson with okay. So one thing about independent random variables is that if you have x and y are independent, then expectation xy is expectation x times expectation y, and this follows from the fact that x and y are uncorrelated. So you can compute, this is going to be the product of the expectations of these things, right? And so we'll show that this limit is what you would expect for a Poisson distribution. But this actually is a bit complicated and messy to calculate, and I'm a lazy person. So I rather, like when I did the Poisson distribution also, when I computed, I said, oh, the moments are a headache to calculate. Instead, let me calculate the expectation of x into x minus 1 into x minus the following factorials. So what I'll do is I'll do that calculation. So let me just define x, let's see, yeah, let me define x, choose beta. So what is beta? Beta is some 1 to, I'll write it like this, you'll see why. It's just a vector, b1, b2, b3. But I'll think of it as a partition with b1 1s, b2 2s, b3 3s, and so on. And oh yeah, so there's one more number that I need to define in the context of. Uh, hmm. So I'll define this to be the product over I, xi choose bi, and I'll compute the limit of this. I'll compute the expectation of this. Okay, so to do this computation, I need to understand a little bit about random permutations. We haven't really looked at them much, have we? So, okay. So I want to know what is the probability. So fix n, and let's say alpha is a partition of n. So alpha is of the form 1 raised to a1. Let's just give ourselves some space here. 2 raised to a2. And so that means a1 1 cycles, a2 2 cycles, and so on. And saying that alpha is a partition of n means that a1 plus 2a2 plus 3a3, all this adds up to n. And I want to know, to start with, how many permutations of the set 1 to n have cycle type alpha. So let's just do a little example here. So I have some 1 cycle. So let's say I have 3 1 cycles. So this is A1 1 cycles in general. Then I have some 2 cycles. let's say A2 2 cycles. Then I have a bunch of 3 cycles. Let's say I have A3 3 cycles, and so on. And I haven't put the numbers here because I want to know how many permutations have this structure. So you see here, basically what you have to do is to find the permutations, you have to put numbers in these places, and then you'll get all the permutations with this structure. So what you can do is you can just start putting numbers however you like. So one very natural way to put these numbers would be to just start with, oops, that's not a good color. Let's just start with 1, 2, 3, 4, 5, 6, 7, or any, you know, any random way of ordering these things, and uh, you will surely get a permutation with this cycle type. So in this case, I got a permutation of 16 with cycle type 1 raised to 3, 2 raised to 2, 3 raised to 3. But then this is not enough, right? Because I could do this number, I could take a different numbering and get the same permutation with this cycle type. For example, if I were to interchange 2 and 3, then I would still, it would be the same permutation. I mean, what I'm saying is that these are 1 goes to 1, 3 goes to 3, and 2 goes to 2. So you could permute. I could similarly, I could just interchange instead of 4 and 5, I could write 6 and 7 here, and I could write 4 and 5 here. Right? So I could write 6 and 7 here, and I could write 4 and 5 here. So I have this permutation. So I could take A1 factorial ways to permute these cycles, A2 factorial ways to permute these cycles, A3 factorial ways to permute these cycles, and so on. But then there's another thing I could do. For example, this 8, 9, 10, I could just move them along. I could write it like this. I could write it 8, 9, 10. So I'm doing the cyclic movement of these things. So then I can also get, you know, and I could do that since it's a 3 cycle, I could also do it in one more way, which is I could write 8 here, 9 here, and 10 here. If I cyclically shift it once more, then I'm back where I started. So that's not going to give me that's not going to give me a different labeling. So what I'm saying is that different labelings can give me the same permutation with this cycle type. But what I'm here, each of these cycles, there are 3 possible ways I can shift the labeling. So it's 3 to the A3, A3 factorial, 2 to the A2, A2 factorial, 1 to the A1, A1 factorial. So what you get is that there are product I to the AI factorial, different labelings give the same permutation with cycle type alpha. This quantity is usually called Z sub alpha in the uh, by so then it turns out that the number of permutations with cycle type alpha is n factorial, the total number of different possible labelings, divided by the labelings which give the same, the number of labelings which give the same permutation. So I get number of permutations with cycle type alpha is equal to n factorial by Z alpha. And so probability that a random permutation has cycle type alpha is just this divided by n factorial. So that's, you know, that's, this is an old formula of, goes back to Cauchy.
Sir, I have a doubt here.
Yes.
Sir, previously when we defined the partition of n, for that deck of cards example, we
Yes.
had considered that the order won't matter. That's why while writing 44221, that was just we were denoting in a decreasing fashion, but
Yes.
order won't be mattering. So right now we are considering the other the different cases where we are flipping 2 and 3 in
Yes. Yeah, that's precisely the point. The order doesn't matter. So if I call this 9, 10, and 8, or I call this 9, 10, 8, it is going to give me the same permutation.
Sir, then why should we consider it in the first case? If
No, so that's what we are dividing by this total number.
okay, so we
Okay,
have
so
to take the case and then we are
I'm
restricted.
over counting to start with. I'm saying we will just put these numbers on these nodes however we like. So there are n factorial possible ways of doing it.
Yes, sir, I got it.
But then how many of them give me the same permutation with this cycle type? Of course, yeah, anyway, I hope that answers your question, though I think, yeah, not exactly what you asked. Yeah. So we can calculate this thing, and the beautiful consequence of this is that the sum over all a1 plus 2a2, if you take this sum over all ways of writing n as a1 plus 2a2, 1 over z alpha, and z is going to be 1 over z alpha, this is equal to 1. The probabilities will add up to 1. So for example, the probability that x1 equals 0, x2 equals 0, xn minus 1 equals 0, and xn equals 1. So this is the probability that you have one cycle of size n. And using this formula, it's a product. What is this z alpha? It's product I to the ai factorial. So only this an is 1, and everything else doesn't contribute. So you get uh, n to the power 1 times 1 factorial. So you get 1 over n. And so this is probability of an n cycle for a permutation of n letters. And if n is even, then what is the probability that you will have k2 cycles? So probability of k2 cycles, this is what is called fixed point free involution. That means it's a permutation whose square is identity, but it has no fixed points. And you can use this formula. It means that you will have k2 cycles. So a2 is k, so you'll get 2 to the power k factorial. And maybe here's another example. The most likely cycle type turns out to be that x1 is 1 and xn minus 1 is 1 and everything else is 0. This turns out to be 1 over n minus 1. This is the most likely cycle type. Its probability is 1 over n minus 1. So that's a little exercise you can try to do later on to see what is the most likely. Okay, so unfortunately, time is running out. I just need to do this one calculation to convince you that the moments of the mixed moments. So what I'm going to do is I'm going to compute En of x choose beta. So what is this? So remember that this is En of x1 choose. So what is x choose? So what is n choose k? Right. So n choose k is n into n minus 1 into n minus k plus 1 by k factorial. And this makes perfect sense if I replace n, which is usually thought of as an integer, by a variable x. Okay, so I can just make sense of this. So I don't have to take x factorial. I can just think of this as a polynomial. So this is x1 choose b1, which means x1 into x1 minus 1, x1 minus b1 plus 1 divided by b1 factorial. That's what this is. x2 choose b2, xn choose bn. Looks horrible, but it turns out that this is actually easy to compute. So it's a little calculation that I've done 100 times. So let's do it once more. So this is sum over all possible a1 plus 2a2 plus nan, uh, whatever it does. I don't care where it stops. Of course, you can't have more than n cycles, but this is equal to n, and then I have to take 1 over z alpha, and then this x1 becomes a1 because I'm saying what is the probability that x1 is a1. So that's 1 over z alpha, and then I have to take a1 choose uh, b1, a2 choose b2. And this whole thing actually has a nice product. This thing, this is also a product, this is also a product. So let me just write it as a product. So this is product I greater than or equal to 0, I greater than or equal to 1. Of course, it will be a finite product. Beyond some point, these terms will not contribute anything. 1 over I raised to ai factorial, and then I'll have ai factorial divided by bi factorial by bi minus ai factorial. And so now some cancellations happen. Um I can pull this bi factorial out. Of course, first what I can do is I'll interchange the sum and product using distributivity. Uh,
Sir, I think that should be AI minus BI factorial.
yes, you're right. So product, and then I will take the sum, and I can pull this bi factorial out, sum over ai. But there is this constraint, right? So I have to be a little careful. Yeah. Yeah, let me just write this down though. So um, I will write here I raised to bi, and then this is sum over. Uh, so I'll just tell you what happens here later. And here I will write 1 over I raised to ai minus bi, and then I have ai minus bi factorial. And the condition here is going to be, yeah, let's just keep the sum outside for now. And yeah, so here we have a1 plus 2a2 plus dot 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 equals n. But obviously I must have ai greater than or equal to bi for each I, otherwise one of these factors will vanish and this whole thing will become 0. So not only do I have ai greater than or equal to bi, I also have that a1 plus, so if I write ci to be ai minus bi, then I'll have c1 plus 2c2 plus 3c3, that is equal to n minus, let's say m is b1 plus 2b2 plus 3b3, will be n minus m. So what I'll get is summation c1 plus 2c2, and then I'll get product I greater than or equal to 1 over I raised to, and here I will get this thing doesn't even depend on the A1, A2 and so on. So I can pull this whole thing out here. And this is just 1 over Z beta. And this is Z. So if I say gamma equals 1 raised to C1, 2 raised to C2, then this is 1 over Z gamma. So this is equal to n minus m 1 over Z. And this is 0 if n is less than or equal to m. So what we get is that this expectation is 1 over Z beta if n is greater than or equal to m, and is 0 if n is less than. So that's the upshot of this whole calculation, that the expectations for these modified moments, so to speak, these modified moments, that is where I replace just powers, is 1 over Z beta if n is greater than or equal to m, and 0 if n is less than or equal to m. And this is exactly what you will get if, so the limit as n tends to infinity of this thing is just 1 over Z raised to beta. But now if you just take the same hold, so if you take x1 is Poisson 1, xi is Poisson 1 over I, x1, x2, x3 independent, then you will get exactly the same this thing, because these will just be the products of the expectation of xi choose bi by the calculation that we had done much earlier, is just lambda to the b divided by b factorial, lambda to the bi divided by bi factorial. So 1 over I raised to bi factorial, and so expectation of x choose beta is 1 over Z beta. So it turns out that the moments of the cycle types, the number of cycles, converge to the moments of this multivariate Poisson with this independent uh, with the independent Poisson, where the ith thing has expectation 1 over I. And I should just give you the reference from which you can clear up the remaining points. So so there's a so this method of moments, it gets a little technical, is described. You need to understand convergence of probability measures, what is called modes of convergence. This is in a paper of Haviland, 1936, and it's cited. I think the authoritative reference is there's a paper. So the most authoritative reference I could find on the subject of cycles in random permutations is a paper called Cycles in Random Permutations, and it's by Aratia and Tavare, Annals of Probability, 1992, and the title is Cycle Structure of Random Permutations. And yeah, so that's maybe I should stop. I'm already a bit over time. So with that, you can sort of fill in all the technical details, but I hope I've already convinced you that this should be Poisson, and you can fill in the technical gaps. Now, Ashwini Sounder is asking, where do we use this concept? So, so this concept, yeah, so surprisingly, this comes up in many different areas. And one notable thing that this came up was in population genetics. So, so there's hmm, yeah. So let's see if I can explain it. I don't understand it that well myself, but let's see. So this I found a very nice article on this. Let me see if I can find it again. Yeah, here's a blog post. So I'll just share that with you. So this is a blog post by Sean Eberhard, and he talks about how this problem is related to another random process, which is uh, separating big sticks from little sticks. So you start with a stick, randomly break it into two pieces, and throw away one half. Then randomly break what's left into two pieces and throw away one half, and so on forever. At the end of this process, you collect all the pieces of stick that you threw and examine them. And almost surely you can divide the stick into two piles, the big sticks and the little sticks, in such a way that the little sticks, even put back together end to end, are much smaller than the littlest big stick. Now you have to parse this carefully, and with the interest, I just suggest you look at this. But this theorem is closely related to the theorem that I have proved. It has to do with random permutation, and here he's going the other way. So he's saying that a random permutation, using that result, he's proving a result about random permutations. It has applications in number theory. Uh, Theorem. This was proved by the famous probability theorist Billingsley. You take a random integer, then you know about the size of factorization. So it's a theorem of Billingsley. Uh, there's also a result about factorization of polynomials. Maybe you can read this. You'll find some very interesting relations to other areas of mathematics. But then bonus at the end. Uh, yeah, there's a link to a blog post of Terence Tao. Yeah, this was Billingsley's theorem. And the added bonus is a comic book by Andrew and Jennifer Granville. So this I just ordered on Amazon today. So it's called Prime Suspects: The Anatomy of Integers and Permutations. A mathematical sciences investigation. So it's actually a comic book. So yeah, so it will take some time to explain where we use it, but you have to, maybe this blog is a good place to start. So you can note down this blog. It's just called randompermutations.com. Okay, so I'll stop. Maybe we have time for more questions. I mean, I have time, but
Yeah, we can go on. If there are more questions, we still have time. If you have a question, you can just send it back.
you're not very clear, Susmita.
I see. We have time for more questions. If you have any question, you can unmute yourself and ask. Maybe Gayatri, maybe we can stop the recording. That will maybe encourage people to ask more questions. Okay,
No,
thank you.
just stop the recording. Yeah.
Yeah, so even if you have stupid questions, clarifications, please go ahead. Okay.
Were there any questions from the Google, the YouTube live stream? I mean, okay.
Okay, so let's thank Amri. And we will be around here for a few more minutes. So whoever wants to ask us anything, go ahead.
Anything at all, yes.
Yeah, you can leave if, yeah. Yeah.
And you feel
yeah,
free
but
to leave.
feel free to leave if you have.
Yeah.
But come back tomorrow, right? Where's the next talk?
Yeah.
Yes, we'll be back. Yes, we'll be back tomorrow at the same time at 7 o'clock.
In the same place too, right? Same link.
Yes. Yeah, the Zoom password and the meeting ID are unchanged.
Yeah. So somehow it seems like attendance is much lower than when we have it in the institute. And
Yes.
yeah.
Yeah.
And
We
people
just
are a
had
lot
some 60
quieter
minutes.
too. Maybe I don't know what's happening.
Yeah.
Yeah, it's hard to
Yeah.
do this.
Maybe if they have an insight into why the attendance, why maybe some of their friends didn't show up. If they have some insight into that, that would be welcome too.
Is this a bad time of the year or something? I mean,
Either a bad time of the year or maybe too many Zoom talks.
that's true. There are a lot of nice talks on Zoom, and
Yeah. So maybe just any feedback would be appreciated.
Chandan Kumar, you were trying to say something.
Yes, ma'am. Good
Uh,
evening, sir. It was a nice
can
talk. Yeah. So my question is, sir, that in this talk I have learned that we are trying to link probability theory with algebra theory some way.
yeah, sure. Yeah, that's one thing we're doing.
Okay.
Yeah.
So is there any possibility of
We're not
linking this
trying to
with?
link. We find that they are linked.
They are linked. Yes, they are linked. So is there any possibility of linking to numerical analysis also?
Numerical analysis, by which you sort of mean like yeah. I'm not sure exactly what you. I mean, when I think of numerical analysis, I think of sort of numerical methods to solve PDEs and things like that. So from that point of view, I cannot really think of anything immediately. But I wouldn't be surprised if you can link PDEs to probability theory. When you look at so here we are looking at a group which is discrete, right? We're looking at this group of permutations,
Yeah.
but sometimes you look randomness on Lie groups, like the orthogonal group. If you have a compact Lie group, then you have probability distribution on it, which you can call uniform. It's invariant under translations of the group. And then some of those properties are definitely related to differential operators that come from the Lie algebra. But I don't, I can't think of
Okay, sir. Okay,
exactly
sir.
how this
Okay.
will work.
Okay.
I wouldn't be surprised if such connections exist. And,
Okay, sir. Okay. Thank you, sir. Thank you very
thank
much,
you.
sir.
Nice question. Well, it seems like there are not too many other questions.
Yeah, I can hear you.
So, well, thanks, Sushmita, for organizing this. And I hope those of you who were here got something out of
Yeah.
it, at least piqued your curiosity. Yeah. that's all I can ask for, because it's difficult to just go to one talk and learn uh, a whole lot, but it should give you some. And I guess there are 3 more talks. Maybe you could just so tomorrow is yeah.
Dheeraj, uh, it's going to be a astronomy talk tomorrow.
Is it related to the Nobel Prizes?
No, not that I know
So
of.
this
But
time the
maybe there
Nobel
are
Prizes in
connections.
physics were for the black holes. And one of the Nobel laureates is Roger
Right.
Penrose, really a mathematician. So of the Penrose tilings.
Right. Right. Uh-huh. Yeah. Let me look at the abstract. Yeah, it's about the evolution of the universe since the Big Bang, using
Oh, okay, okay.
codes. Yeah. Okay. So should we say it's over? Yeah. I liked your talk a lot. Not only was it good, it was also technically there were no glitches.
Well,
It
I
was
mean, I
all
left out the
working very
hard
nice.
parts of the proof, which is the analysis that goes into Haviland's theorem and so on. Yeah,
Right.
I hope it was
Okay. Yeah.
persuasive.
Thanks a
Yeah.
lot. And yes. Yeah. Okay. So see you in one of these talks in the next 3 days, Ambi. And hopefully all of you will come back for all 3 talks and bring more of your friends.
Yes. Okay, then I guess it's dinner time.
Oh,
Bye.
yeah. Okay then. Bye bye.
Okay,
Bye.
bye.
Yeah.
Hey, Gayatri, are you still there? Gayatri? Ha. Okay. So, one thing that maybe we want to test out tomorrow. So there was those issues with the